So in this lecture video, we'll try to understand how to plot Bode plot. Bode plot consists of two plots, magnitude plot and phase angle plot. Magnitude plot is a plot where along x-axis we consider log of omega and along y-axis we consider the magnitude of the given expression. In phase angle plot, along x-axis we'll consider log omega and along y-axis we'll consider phase angle. So the first step whenever an equation is given to us is to check whether the equation is in its standard form or not. So the standard form of g of s into h of s is given by the expression g of s into h of s equals k into 1 plus t1 of s into 1 plus t2 of s etc. divided by 1 plus ta of s tas into 1 plus tbs etc. So whichever equation is given to us, it should satisfy the standard form. If we observe, the given equation is already in the standard form. The given expression whichever we have taken is already in the standard form. Therefore, g of s into h of s equals 10 divided by s into 1 plus 0.4s into 1 plus 0.1s is already in its standard form. Next, we replace s by j omega. So when we replace s by j omega, g of s into h of s becomes equal to 10 divided by, in place of s I'll be replacing it with j omega into 1 plus 0.4, again we have s, so in place of that I'll be substituting as j omega, again we have s here, so 1 plus 0.1 into j omega. Using the above expression, we will be plotting something called as corner frequency. So we already know the standard form of g of s into h of s. Normally we write the standard form of g of s into h of s will be in the form of 1 divided by 1 plus s into t. So this will be taken as standard form. And also we already know that omega is equal to 2 pi divided by t, or I can also write omega is inversely proportional to time period. So because of this inversely proportional to time period, omega is inversely proportional to time period, we consider omega is equal to 1 divided by t. Therefore, the corner frequency 1 will be equal to 1 divided by the first corner frequency which we consider here is 0.4, because here if we observe 1 plus s into t1 is 0.4, hence in place of t we will be substituting as 0.4. So 1 by 0.4 is 2.5 radians per second. Similarly, we will see second corner frequency. To check second corner frequency, we will take the second term here, 1 divided by 1 plus 0.1 into s. It is in the form of 1 plus s into t. So in place of t, we will be substituting as 0.1 here. So 1 divided by 0.1 will yield us 10 radians per second. So these are the two corner frequencies. From the expression given to us, that is the first equation, 10 divided by j omega into 1 plus 0.4 into j omega into 1 plus 0.1 into j omega, we can find that there are three terms. The first term which we consider is 10 divided by j omega. So this is the first term. The second term which we consider is 1 divided by 1 plus 0.4 into j omega, that will be our second term. The third term which we have is 1 divided by 1 plus 0.1 into j omega. So these are the three terms which we observe from our equation number 1. By using the three terms, we plot this table. So in the table, it consists of term which we have taken. There are three terms, 10 divided by j omega, 1 divided by 1 plus 0.4 into j omega, 1 divided by 1 plus 0.1 into j omega. We plot something called as corner frequency, which we have already found out. We plot something called as slope and change in slope. To find out slope, we will be using this table. So if we have s term in our equation, then the slope is 20 decibels. If we have 1 divided by s term, that is s term is in the denominator, the slope which we consider is minus 20 dB. If we have s square term 40, if we have 1 divided by s square term, we will take minus 40. So this table we have to remember. So for the first case, that is the corner frequency for the first term, because this is not in the standard form, we will not be having any corner frequency. So we don't have any corner frequency here. Next, to find the slope, because this S term, S is equal to j omega, we already know that. So because S term is in the denominator, this is in the form of 1 divided by S. So if it is in the term of 1 divided by S, the slope will be minus 20. So we'll consider the slope as minus 20. Because before this we don't have any other term, there will be no change in slope, so there will be no change in slope, we'll put a dash there. Next, the next term, 1 divided by 1 plus 0.4 into j omega. So if we observe, previously we have found out what is the corner frequency for 1 divided by 1 plus 0.4 into j omega term. So the corner frequency which we had found out was omega c1 will be equal to 2.5 radians per second. That was the corner frequency which we had found out. Similarly, if we observe how to find out the slope, here if we observe in this particular term 1 divided by 1 plus 0.4 into j omega, again this S term is at the denominator. If the S term is at the denominator, then definitely we have to take the slope as minus 20. Next, a change in slope will be equal to the summation of these two slopes which we have, minus 20 plus of minus is minus again minus 20, which is equal to minus 40. So that will be the change in slope. Similarly, the next corner frequency. For the next term, the corner frequency which we had found out was 10 radians per second. To find out slope, again if we observe we have an S term at the denominator. So if we have S term at the denominator, we have to take the slope as minus 20. So again I'll consider minus 20 here. Again the change in slope will be equal to minus 40 plus of minus 20. So minus 40 plus into minus is minus again, minus 20 will be equal to minus 60. So this is the change in slope. Always the corner frequencies which we consider should be in ascending order. So this point has to be remembered and it's very important. The corner frequencies which we select should be in ascending order. So in order to these two corner frequencies which we have got, we always consider lower frequency and higher frequency. So we can consider lower frequency any term which is less than 2.5 radians per second, and we can consider higher frequency any value which is greater than 10 radians per second. But when we are choosing lower frequency, we should avoid taking 1 radian per second because log of 1 will be 0. Hence, normally we consider lower frequency as 0.1 radians per second and higher frequency as 100 radians per second. And again, this is not mandatory that we have to consider only these two. We can consider any value which we wish. To find magnitude, we consider the 4 frequencies. The first frequency we consider is lower frequency, which we have considered as 0.1 radians per second. And the second frequency is the corner frequency 1, which is 2.5 radians per second. And third frequency is 10 radians per second. And finally higher frequency, which we have considered as 100 radians per second. So by considering these 4 frequencies, we'll calculate what will be the magnitude of it. So for the first frequency, when omega is equal to omega L, which is equal to 0.1 radians per second, magnitude will be equal to 20 log of the first term, modulus of the first term. The first term is 10 divided by j omega. So modulus of 10 divided by j omega will yield us 20 log of 10 divided by omega. So what we do is we'll apply this 0.1 in this omega. In place of omega, we'll replace it with 10 divided by 0.1. So the final answer which we get is 40 decibels. So this is the amplitude when omega is equal to omega low for 0.1 radians per second. For the next case, when omega is equal to omega c1, whose value is 2.5 radians per second, magnitude will be equal to 20 log of 10 divided by j omega, modulus of 10 divided by j omega. Again, the modulus of 10 divided by j omega will be equal to 10 divided by omega. So in place of this omega, we will be substituting as 2.5 radians. So 20 log of 10 divided by 2.5. This will yield us a value of 12 decibels. So amplitude or magnitude at omega c1 is 12 decibels. Only for the first two cases we'll be using this formula 20 log of the first term. Whereas to find out the amplitude or magnitude for the third case is omega C2, amplitude with respect to omega C2, we'll be using this formula. From here onwards we'll be using this formula. So the amplitude will be equal to change in slope of previous frequency into log of current frequency divided by previous frequency plus amplitude of previous frequency. For example, when omega is equal to omega C2, amplitude of omega C2 will be equal to change in slope of previous frequency. So the change in slope of previous frequency is change in slope of omega C1. So change in slope of omega C1. Change in slope of omega C1 multiplied by log of the current frequency. The current frequency which we have considered is omega C2, log of omega C2 divided by the previous frequency which we had considered was omega C1, was the previous frequency, omega C1 plus the amplitude of previous frequency. The amplitude of previous frequency which we have found out was A of omega C1. So using this formula we'll find out the next amplitude value. So A of omega C2 will be equal to change in slope of omega C1. According to the table which we had considered, change in slope of omega C1 was minus 40 decibels, minus 40. So we'll consider here as minus 40 into log of omega C2. Omega C2 value is 10 radians per second, which we had found out. 10 divided by previous omega C1 value is 2.5 radians per second. So divided by 2.5 plus A of omega C1. The previous amplitude of omega C1 was 12 decibels. So we'll consider that 12 decibels here. So when we solve for this, we will be getting as minus 12 dB, approximately minus 12 dB. You'll be getting as 11 point something, minus 7 point something. We can approximate it to minus 12 decibels. Similarly, to find out the amplitude at omega h, we already know that omega h is equal to 100 radians per second. So we'll be using the same formula. So amplitude will be equal to change in slope of previous frequency. So change in slope of previous frequency for this omega h is omega C2. So change in slope of omega C2 into log of current frequency. Current frequency is omega h divided by previous frequency. Previous frequency to this omega h is omega C2. So omega C2 plus previous frequency amplitude. Amplitude which we have got for previous frequency is omega A of omega C2. So A of omega h will be equal to change in slope of omega C2, which we had found out was change in slope of omega C2 is minus 60. So we'll use that minus 60 here. Minus 60 into log of omega h divided by omega C2. Omega h value is 100 radians per second divided by omega C2 value is 10 radians per second plus A of omega C2. A of omega C2 which we have got as minus 12 dB. So when we solve this, we will be getting as minus 72 decibels. A of omega h is equal to minus 72 decibels. From the calculation, we have got when omega is equal to 0.1, the amplitude which we had got was 40 decibels. When omega is equal to 2.5, the amplitude which we have got is 12 decibels. When omega is equal to 10 radians per second, the amplitude which we have got was minus 12 decibels. And finally, when omega is equal to 100 radians per second, we have got as minus 72 decibels. So by using these values, we will plot the magnitude plot.